It's a great pleasure and an honor to be back. I have very fond memories of my past time in Lausanne, and it's also been, every time I visited, it's been very inspirational and good mathematics has come out. So it's something of a coincidence that my title begins with de Rham. Actually, what happened is Philippe sent me the invitation for this, and I thought, I've been working on something that has de Rham theory throughout it. That would be a perfect subject to talk about today. So I'm going to speak on de Rham theory, values of L functions, or L values, and non-split extensions. And I'm going to start with a story that may be familiar to some people, but hopefully by the end, I'm going to get to a theorem that's just been proved. And along the way, I'm going to sort of trace the role that de Rham theory plays in all of that. Right. So L values. Let's see. So if we're going to talk about values of L functions, we should probably begin with the Riemann zeta function, something that we're all hopefully familiar with. So initially defined as just a simple series of sum over the integers of n to the minus s, which is absolutely convergent for the real part of s larger than 1, and in fact can also be expressed in that same region as an infinite product, kind of a reflection of the unique factorization of integers. It has famously has an analytic continuation to all of the complex numbers, aside from a simple pole at the one point s equals 1 with residue 1. And there's even more structure if we make a slight modification, which will be kind of important, some gamma factors and a few other things. This modified function satisfies a very simple functional equation relating xc of s to xc of 1 minus s. And the celebrated Riemann hypothesis would be that the only zeros of this xc function lie at the real line with real part equal to a half. But I'm not going to be interested with any of those zeros today. I'm going to be interested in actually some trivial zeros of the Riemann zeta function that are sort of influenced by this gamma factor. So you should remember this. All right, so what about values of L functions? Well, I guess here it might not be a bad idea to begin with the famous Basel problem, which was to evaluate the sum over the reciprocals of the squares of positive integers, famously resolved by Euler. And we can think of that as the value at 2 of the Riemann zeta function. This is a special case of a much more general expression that tells us that the value of the Riemann zeta function at positive even integers is a rational multiple of a power of pi. And the particular rational multiple involves the Bernoulli numbers. We can clean up the formula using that functional equation from the previous slide, and we get this nice expression that the Riemann zeta function at negative odd integers is a rational number. And this is kind of, I think, something that whenever number theorists see sort of a particularly nice function like the Riemann zeta function taking algebraic or rational numbers at algebraic or rational points, they sort of say, aha, something interesting must be going on. And here's some examples of what those rational numbers are. There's a famously that zeta of minus 11 has this 691 in the numerator, which is something that shows up in work of Ramanujan. And I'll say something about that a little bit later. Using the functional equation, though, I want to go back to this. So the gamma function has poles. It has poles at odd integers. And so when s is odd or even, then gamma of s over 2 will have a pole. But if this product is analytic, that means there must be a 0 somewhere compensating for that pole. And so the zeta function actually vanishes at the negative even integers. So it's a nice rational number at the negative odd integers, but it's vanishing at all the negative even integers. And then there's a sort of collection of values that I've left out. The value of the zeta function at odd positive integers, that's an extremely interesting problem. What should be the kind of the nature of these numbers? And that's very much an open problem. I think for that, and there's interesting results, but I'm not going to be able to say anything about those. All right. These features of the Riemann zeta function, the rationality of values at integers, the existence of zeros for some systematic reason are shared by many of the other Dirichlet series that are of interest in number theories, theorists. The Dirichlet L functions, where one begins with a character, a finite order character of say, modulus n, and you look at a series that's much like the Riemann zeta function. The only thing you've done is modified that initial coefficient by the value of the character. It shares many of the same kinds of analytic properties. And the case that I'm going to pick on today is when that character is quadratic, and maybe even. So by even, I mean its value on -1 is +1. So there will also be characters where this value on -1 is -1, and we call those the odd characters. And there's some qualitative differences between those L functions. The even quadratic ones are more sort of closely parallel the Riemann zeta function. So for such characters, the L0 of chi is 0. Again, partly because of a pole of the gamma function at 0. There's a functional equation, and across the functional equation, one gets a value for L1 of chi. And one of the expressions for that is as a sum over the group that we're looking at, Z mod nz, or the multiplicative elements mod Z mod nz, the value of the character, and then multiplied by a log of a certain transcendental function, in this case, the exponential function, but evaluated at some particularly interesting point. This is an interesting, and sometimes this is called an explicit formula. And when we know them, they're often often useful, as we'll see. Similar properties exist for other L functions, the L functions of elliptic curves, the L functions of automorph forms, like modular forms and things like this. So all the L functions that people like me like to talk about share similar properties. And so why am I telling you this? So is there any significance to these L values? And the answer is that yes, at least we expect so, and in some cases we know so. Today I'm going to pick on not so much the significance of the values, say the Riemann zeta function at odd integers, odd negative integers being Bernoulli numbers or something, but I'm going to pick on the vanishing, this sort of systematic vanishing at the negative even integers. Or really, I'm going to pick on the vanishing of L0 chi for an even quadratic character. And I'm going to explain to you how de Rham theory sort of illuminates the significance of this value. So over the years, reflection on these values have led number theorists and algebraic geometers and arithmetic geometers to expect that this kind of vanishing should reflect the existence of non-split extensions in certain categories. So we can, and the categories that people talk about are the categories of mixed Hodge structures. The categories for people like me are p-adic Galois representations. And if you're very ambitious, and this is the last time I'll say this word, mixed motives. The extensions of Galois representations are have a considerable utility and can be combined with congruences. So we're looking at p-adic Galois representations, so we can do congruences mod powers of p, and ultimately we can take the extensions that we get from vanishing and use them to explain some of the other values. For example, the fact that zeta evaluated at -11 is 691 over 32,760 can tell reflects many things. One of the things being that 691 actually divides the order of a certain piece of the class group of the field that you get by joining the 691st roots of unity. And so this means, in particular, that unique factorization fails in a very precise way in this field. And so there's some sort of more complicated arithmetic. And complicated should really just mean interesting. So what I'd like to do is pick on the special value formulas for quadratic characters. So the situation I'm going to put myself in is I'm going to look at a character modulo a prime that's congruent to 1 mod 4. Why a prime congruent to 1 mod 4? Because then -1 is a square mod 4. And so for a quadratic character mod n, the quadratic character will always be even. So chi of -1 is 1. So I'll look at the unique quadratic character mod n. That's non-trivial. It'll be an even quadratic character. I'll write zeta of n for this particular nth root of unity. And then I can rewrite the formula that I told you before for L1 and chi using zeta of n. And as I mentioned before, the functional equation is telling us that we actually have this sort of 0 at s equals 0 for this L function. And it also tells us that the derivative of the 0 is related to L1 of chi. So it has a very nice formula. All that's happened is the power of pi has dropped out. And we know, actually, in both instances, that these values are not 0. There's something that goes into that. I mean, it's not obvious that a sum of logarithms of numbers won't be 0, right? The numbers could have product equal to 1. So that there is some input there. Just so that you know, this tau chi is the classical Gauss sum. Here's an expression for it, and probably the most important thing to know is just it's a number whose absolute value is the square root of n. So it doesn't affect vanishing or non-vanishing at any point in any of these formulas. All right. So what I want to do is I want to explain that the existence of a non-trivial extension in some category that's I sort of claiming that it's related to this 0. What it's really going to be, it's going to be non-split precisely because of the non-vanishing of this derivative. So that's really just saying what I'm about to say. So what is that extension? So we're going to start by moving into topology. So there's our setup as before. And we're going to take a very simple situation. We're going to take an ambient space that's just the complex plane minus 1 point. And then I'm going to take the primitive nth roots of unity inside there. That's a 0-dimensional subset. And I'm going to look at the relative cohomology. So this is just singular cohomology. I'm going to look at the relative cohomology of this topological space relative to these finite collection of points. So there's an exact sequence which has its quotient, in this case, the usual cohomology, and the kernel is surjective image of the H0 of our points. And so this is all very simple. Since we've only removed a single point, the cohomology is actually a 1-dimensional Q space, generated by a dual of just the loop about 1, loop about our point. And so I'm going to take that, and I'm going to look at the extension I get by quotienting out by some map on some quotient of this kernel here. I'm going to take thinking of this as just functions on the points of z. I'm going to look at the evaluation on those functions weighted by the value of the character. So the evaluation on those points weighted by the value of the corresponding value of the character. And so that's going to be, because it's a quadratic character, it's a map to Q. And I actually get a short exact sequence. The reason that this map is injective is that the kernel here is just the H0 of y, which is the value, which is just Q, because it's connected, embedded diagonally inside there. And so the evaluation at chi vanishes on that. Yes. Oh, so this is EV. Sorry, it's EV of, I'm thinking of H0 Z of Q as sort of functions on Z valued in Q, since Z is a finite set of points. And so if I evaluate that, I'm evaluating sort of at the point A, which is indexing that Z, and I'm weighting it by the character. So if this were the diagonal, if I had the function that took on the constant at all of the points, then the evaluation at A would be that constant, and I would be multiplying by the sum over the character. And the sum of the characters is 0 because it's a non-trivial character. Okay, so this is an extension of vector spaces. Extensions of vector spaces are not particularly interesting unless they also have some additional structure. And that's partly where de Rham theory is going to enter the picture here. Right? So we were talking about singular cohomology, and of course, the sort of one of the strengths and virtues of de Rham theory is it allows us to express singular cohomology in terms of differentials. And so if we have a smooth manifold, we have the singular de Rham isomorphisms that compare in a very functorial way the singular cohomology, at least with coefficients in C, with the smooth de Rham cohomology. And that works fine also for relative cohomology. And very explicitly, de Rham cohomology is just computed by the smooth de Rham complex. I'm assuming everything is, all my manifolds are smooth. And then later, we're going to have to refine this using Hodge theory. But already then, so we can take our singular cohomology sequence that we're looking at, look at the corresponding de Rham cohomology sequence. And we had one particular class, and very explicit class in here related to the loop around s equals 1. And we can identify the differential that gives rise to that class in de Rham cohomology very explicitly as 1 over 2 pi I of dz over z minus 1, where I'm using small z as the sort of point on the complex plane. Sorry. And under these de Rham singular maps, these two classes are identified. So one of the features is that we can be very explicit with this comparison in this particular case. And that's going to be important. And so then we can do the same construction that we did before. We can make the de Rham extension that using the de Rham class and same evaluation map. And this is nothing more than taking the sequence that we constructed using singular cohomology and extending scalars from Q to C. So we're still just vector spaces. So where's the additional structure? Well, we're almost there. De Rham theory comes equipped with a filtration, the de Rham cohomology. In this case, the Hodge filtration. This is because, in particular, in this situation, we're dealing not just with smooth manifolds, but with complex manifolds, and the Hodge filtration is particularly nice in that case. So you can compute the de Rham cohomology using holomorphic differentials. So there's a complex that one writes down, just the usual de Rham complex. And then you take the cohomology of the complex, and that's the de Rham cohomology of your complex manifold. That complex has a sort of a very simple filtration where I just replace the first t-1 terms with zeros, and that gives me the p part of the filtration. And the image of the cohomology of this sequence inside the cohomology of this complex is what we call the de Rham filtration. In the case that we were looking at, this takes a particularly simple form. The de Rham filtration turns out to be the entire cohomology in the case of Y. It's a one-dimensional space in the case of the relative cohomology, still generated by dz over z minus 1. The point is that when we're looking at differentials here, we're looking kind of at differentials that vanish along z, but since z is zero dimensional, the restriction of this differential is zero. And then there's, because z is zero dimensional, the f1, in fact, is zero. And so this gives us a filtration and on this extension. So this extension is right here is some two-dimensional vector space. And the image of this is going to be some one-dimensional subspace. And so that's giving us, in this simple case, a filtration. That's still not enough, because this is visibly an extension of filtered vector spaces, right? I mean, if you believe this top line, this filtration is mapping to the filtration there. So it's still not an interesting extension. We have to have one more player before something interesting shows up. And that's the action of complex conjugation on the spaces. So complex conjugation acts on y and on z. Fixes one, so certainly acts on z, and it acts on c. It's in a smooth map on both of these spaces. This is sort of a hint for what's coming ahead. This is reflecting that both of these are actually very simple algebraic varieties defined over a field fixed by complex conjugation. So this gives us an action on this action on the spaces, gives us an action on the cohomology groups, and it's compatible with that de Rham isomorphism, the way you compare the cohomology groups. So I'm going to call this action phi infinity. So here's the situation now. We have our singular extension that came out of singular cohomology, and it's an extension not only of vector spaces, but of vector spaces with a action of complex conjugation from the way. And if we tensor that with Q, then or over Q with C, then the de Rham theory gives us an extension of filtered C spaces that interacts nicely with the complex conjugation. And now what we're really asking, we can ask now, is there a splitting of the first sequence, the singular sequence, the sequence of complex of Q spaces with a complex conjugation? Is there a splitting that's compatible with the filtration on the extension? And this is where we start to see interesting things showing up. So the answer is no, actually no such extension exists. The reason that no such extension exists, I'm going to claim, is that the L value, L1 of chi, is not zero. And what we're actually going to see, it's because the non-splitting of this extension is going to be related to that very explicit formula for L1 of chi that I wrote down. So here's how it goes. Let's just do it. So if we look at the action of complex conjugation on our explicit de Rham cohomology class, it's just going to replace z with z bar, because that's what complex conjugation is doing. So that's another smooth differential. And we have this relation. We can check, this is a nice simple formula. One can check that the sum of these two differentials is just d of this nice function, the log of the absolute value of z minus 1 squared. So that means that the sum of these two differentials is 0 in H1 de Rham of y. But it's not 0 in the relative cohomology, because this function is not vanishing on the points of z. So it's not in the relative H0. So this is a log of absolute value of z minus 1. It's a nice smooth function on c minus 1, but it's not a smooth function that vanishes on our roots of unity. So even though we have this relation, we're not getting a non-zero class, or not necessarily getting a non-zero class in the relative cohomology. And in fact, that means that the class 1 plus infinity times the phi infinity times this class is actually the image of the log, the absolute value of z minus 1, keeping just 1 over 2 pi I there, inside H0 of z, image under the boundary map from this cohomology group to this cohomology group. And then, so let's just check then what's the image of this class under our evaluation map. So we're just evaluating our function at our points, which is our roots of unity. And so we get visibly this expression that we've seen before as an explicit value for, or explicit formula for the derivative at 0 of L0 of chi, or really the value at 1 of chi. And since we know that this is not 0, we've just seen that this extension is non-split. Okay, so we can reinterpret this as saying that this singular extension, together with the filtration on its de Rham realization, so what we got from sending scalars to C, together with the action of complex conjugation, they actually define a class in some category of mixed Hodge structures. The plus here is to say that it's an enriched category, meaning we're keeping track of this action of the complex conjugation. And in fact, that the non-vanishing of this derivative, or of the value at 1, tells me that this extension of mixed Hodge structures is actually non-split. And this is a kind of phenomena that we expect to see in great generality in number theory. Whenever sort of an interesting L function has a 0, there should be a non-split Hodge structure that sort of explains that. And this would be the instance when when an elliptic curve, when its L function vanishes at the central critical value, there should be non-split Hodge structures coming from the expected point, for instance.
But you speak of vanishing, and here non-vanishing.
Thank you. Yeah. So really what's happening, the L0 of what's behind all this is L0 of chi was 0, and it's 0 of order 1. And yeah, I'm getting a one-dimensional thing. Yeah, this is, well, let's move ahead, but yes, so fair point. I went through that long sort of elementary case just because I want to say that that's the template for a large number of similar kind of extensions and constructions. And so, for instance, we can replace singular cohomology with étale cohomology. In our particular case, here's the underlying algebraic varieties. I'm going to use the overbar to denote their extension to the algebraic closure of Q. We can look at the étale cohomology. We can make exactly the same construction. We now get an extension of Galois representations. So there's an action of the absolute Galois group of Q on all of these spaces. And we can still be very explicit with the class that we're choosing to generate on this side. There are comparison theorems for singular and étale cohomologies, and we can choose this generator in such a way that it maps up with the generator in singular cohomology. And then as underlying QP spaces, we've just constructed the extension that takes our singular extension and extends scalars to the p-adics. All right, so this gives us an extension in a category of vector spaces over the p-adics with a Galois action, the Galois group of Q. And I can also think of that as a class in a Galois cohomology group. So this denotes Galois cohomology or group cohomology for the Galois group Q. And my coefficients here, there's the character that's Galois character associated to the quadratic character, and the cyclotomic character is giving me the action on roots of unity. And that's related to this -1 that's showing up here, which is sometimes noted as a Tate twist. So this the Galois group here, this -1 means the Galois action is by the inverse of the cyclotomic character. So we have that. How do we can ask whether that's a non-split extension, and the non-splitness of it we again can prove by again going back to de Rham theory. So I'm going to invoke p-adic Hodge theory, which might be less familiar to people than classical Hodge theory, but once again it allows us to take a cohomology theory and relate it to de Rham cohomology. In this case, it's algebraic de Rham cohomology, but that's not very far from classical de Rham cohomology. And I've put on these slides some definitions, but we don't actually need them for what we want to do. I just want to say that there's some functor that's taking this étale cohomology to algebraic de Rham cohomology in our setting. And so again, exactly, all I've done is sort of take that diagram where I had singular cohomology in the top line, and I've replaced it with sort of the image of my étale sequence under that functor. And now we've got the same kind of de Rham sequence, only now it's algebraic de Rham cohomology. So instead of being over complex vector spaces, it's vector spaces over, in this case, the p-adics. But everything is expressible in terms of algebraic differentials. And in fact, the corresponding differential here is just a dx over x minus 1. So the only thing that's disappeared is the 2 pi I. And that has a p-adic shade in this sort of T bar. Well, I'm not telling you, Bart, which was some element of this ring B de Rham, which is the p-adic version of the complex numbers. So the complex Hodge theory, you tensor up with C. Here we have to tensor up with a different ring. And where we might have put a 1 over 2 pi I before, we now just have this T bar. That's all. Again, this is Rham theory. They come equipped with a Hodge filtration. So this bottom sequence is an extension of filtered vector spaces. But there's more than just a filtered vector space. There's again sort of a replacement for complex conjugation, a phi operator that's now a Frobenius operator in this case. And it's not an involution, but it's still a fairly nice kind of operator. And so what we have is that we have our extension of Galois representations that came from étale homology. And it turns out there's this very nice equivalence. That sequence is non-split if and only if the corresponding algebraic Hodge theory sequence with its filtration and its action of a Frobenius is non-split. And so there's, we have this Galois group, which can be quite complicated or mysterious in terms of its actions, and we've sort of reduced some statement about extensions in that category to a linear algebra or a semi-linear algebra statement because of this operator here. And now exactly the same calculation that we did before shows that this is a non-split extension. There's no such extension splitting of that bottom sequence. And why is that true? Well, it's true because an L value is non-zero. This time it's not quite a complex L value. It's a value of what we call a p-adic L function, which is some function that interpolates values of classical L functions. And the reasoning is virtually the same. One can be very explicit about the action of our phi operator on the de Rham homology class. It basically has to do with replacing x with x to the p. Hopefully I've written this calculation correctly. You get some, and you want to find a primitive of that differential, and formally it should look like this logarithm. And you can make that quite precise. There's a theory of integration in these spaces with p-adics. And in fact, one can then substitute that log function into the evaluation map, and you get an expression that looks a lot like what we saw before, only somehow I've decorated the logarithm with p. That's not the base p, that means the p-adic logarithm. It's the function that's given by the same convergence series. So you write down the usual Taylor expansion for log of x plus 1.
Before to make the analogy perfect, you were showing before that also the derivative in the complex analytic case. You were showing the derivative.
Yes.
Where is the role?
So the derivative is a little, yeah. So there isn't quite the derivative here. Yeah. So maybe the derivative before, because of the functional equation, was also related to L1 of chi, and here I'm not really just seeing the L1 of chi maybe I was pressing the point a little too much before. But and so this can be interpreted as some L value being non-zero, okay, and an extension being non-split in a certain category. I'm trying to keep track of my time. Okay. If you want to be fancy, or if you've seen words before and you want to know what they actually mean, what we've done in that previous slide was calculate the block-Kato logarithm of this class, this Galois cohomology class, and shown that it equals LP of 1, chi. So if you've seen this, people talk about block-Kato logarithms in a number theory seminar or something like this, they're really talking about a de Rham calculation, and very much like the one that we just did. And I just, of course, want to emphasize that just as in the mixed Hodge structure case, it was really de Rham theory that drove the proof that this extension is non-split. At least this particular proof of that fact. All right, both of these examples illustrate a template for linking L values and extensions. And I want to give you some examples, some additional examples, including one that has been useful recently. The template is the following. We had a variety Y, we had a subvariety Z, and it's of codimension 1. And then we looked at at least I'm going to assume that for simplicity. And so then we looked at this kind of relative cohomology sequence for various cohomology theories: singular cohomology, de Rham cohomology, étale cohomology, algebraic de Rham cohomology, and we have comparison isomorphisms between all of these theories. And then we take some explicit class, C, maybe inside our cohomology, and that gives us a line. And maybe it's a particularly nice line. Like if in the Galois world, it might come with a particularly nice action of the Galois group, like the -m Tate twist. And then we sort of pull back that line, and then we push out by some linear functional on the bottom term, and so we get an extension. So this is a pull back, push out sequence in cohomology. And we can do this sort of, the idea is that to do this compatibly in all of the cohomology theories, and then to use those comparison theorems and all the various structures on the cohomology theories to derive some sort of consequences for this extension. So, so maybe in the de Rham world, this class is given by some explicit differential, ideally, maybe holomorphic, in such a way that it's annihilated by some polynomial of the corresponding Frobenius, either I think of the complex conjugation as sort of like a Frobenius for the real numbers. So maybe that's a derivative of some. So we apply that polynomial to our class, and we get that it's our differential, in fact, and then it's the derivative of some omega prime. And then we can see that this extension would be non-split in whatever category we're working in if the image of this class, its restriction to Z gives a class in here. We can look at its image in V, and we can ask whether that's not zero. So that's a criterion for this being a non-split extension. And we can sometimes find an explicit formula for this by pairing the restriction of our differential to Z with some other differential on Z that picks out V. So under the Poincaré pairing or something, then this derivative is in the dual of this space V. And so then in the de Rham world, this can be thought of as just saying we're taking an integral over Z of omega prime against eta of V. And in an ideal situation, this is up to some factors, perhaps an L value for this vector space V evaluated at some point M. That's exactly what we did, in fact, in those two situations. And so I want to do that in a couple of more situations. So now I'm going to move into number theory. So I'm thinking this is sort of a colloquium talk where I can get gradually more and more sort of, sort of focused on the things that I do as we go along. So now I'm going to let K be an imaginary quadratic field. Take Q adjoin square root of -1. Psi is going to be a finite order Hecke character of K. So it's just the analog of a Dirichlet character. And so now the situation, I'm going to study the L values of this Hecke character. And the situation, the geometric situation, is I'm going to take a modular curve. In this case, so that's the upper half, complex upper half plane modded out by some congruent subgroup, like some finite index subgroup inside SL2Z. Not any finite index subgroup, but the congruent one. And then for Z, I'm going to take a collection of CM points. So these are going to be points in the upper half plane, which I can think of as just elements of K. So these are going to be CM points associated to the field K. And those are particularly nice. They are, well, the modular curve can be thought of as a variety over Q, a algebraic curve over Q, and these CM points are algebraic points. They're defined over some number field. This is the theory of complex conjugation, one of the most beautiful parts of number theory. Okay, so in that same situation, then we can look at exactly the same kinds of sequences that we looked at before. What am I going to take for my special class C is I'm going to take the differential associated to a holomorphic Eisenstein series. So the holomorphic differentials on the modular curve are of the form f of tau d tau, where f is a weight 2 modular form. I'm just going to take a particular weight 2 Eisenstein series. That's going to give me a differential on my modular curve. I'm taking the open modular curve, so I haven't compactified. And so that's my, and then I can actually analyze everything I want to know about that differential. I can see the Galois action. I can see the fields of rationality for it, and all of this. I can be very explicit in exactly the same way that we were explicit for dz over z minus 1. So this is something differential which we can be very explicit about in terms of how it shows up in all the cohomology theories. And what on the left-hand side, I've written this evaluation of psi, which is analogous to the evaluation of character, and it's meant to be of chi I had before. So these points z that I would choose, they're identified with the points of a ray class group of the imaginary quadratic field, and my character is a character of that group. That's part of the theory of complex multiplication. So I can talk about this evaluation map, and I get this extension in all of my categories. And the interesting thing is I can do, because I can be very explicit with the Eisenstein series, I can do exactly what we did before. In the case of complex conjugation, if I replace my Eisenstein series with 1 plus phi of e, or phi of infinity here, acting on the Eisenstein, it's the derivative of a weight 0 Eisenstein series, a smooth C infinity function. And there's a formula, which I'm writing as an integral over z, just to be kind of suggestive. It's, of course, z is 0 dimensional, so it's a sum. So this evaluation of this primitive would be the evaluation of the function at the various taus, complex, the CM points, the taus in z, may be weighted by our Hecke character. And it turns out that sum, for the right, you choose your Eisenstein series correctly, is an L value of the Hecke character. And so what one sees here is that this extension is non-split in our various categories, precisely because L1 of one of these Hecke characters is not 0. So it's exactly the same picture as for Dirichlet series. We can, there's also a Galois version. Not surprisingly, I had all those question marks. This, in fact, gives, and at L1 of psi is a finite order guy. So, oh, yeah. a
What
non-true.
is the normalization?
This case, since it's finite order, it's S goes to 1 minus F.
Okay.
I should say that the Galois version is really, this is sort of a Galois realization of a construction in the p-adic world due to cats. And that will come back. We can do higher dimensional analogs where we take V, in fact, to be the modular curve, and we embed it diagonally into, say, into two products of the modular curve here. And now I'm going to take on my H2. It's the H2 of a product of two curves. So I have the Knuth formula. I can write down holomorphic differentials by just taking two holomorphic differentials, one on each curve. I'm going to take two Eisenstein series. The projection map from the H1 of Z, I'm going to take the usual projection associated with a modular new form. So using, say, Hecke I operators, I have such a projection. This is supposed to be a two-dimensional space now. And so this is the extension is now a three-dimensional object. Again, these are Eisenstein series. I can be very explicit with them. The Galois action is given by some character and then the -2 power of the cyclotomic character. And the explicit formula is just the Rankin-Selberg formula for an L value. In fact, you get a product of two L values. I'm subsuming one into the star because it's really a period in this case. And the relevant L value for the extension is the L value of F at the character chi evaluated at 2. And so the non-vanishing of this L value, so you have to prove that the star isn't 0, but you can make a choice so that it isn't. So the non-vanishing of this L value is then telling me that the non-vanishing of this sort of three-dimensional extension in whichever category. So the Galois version of this, the L function gets replaced with its p-adic L function. There are many such formulas that arise in the world of modular forms. Here's a sort of newer one, or at least one that people haven't paid as much attention to. So now, you kind of see a pattern here, right? So in each of these examples, the larger variety is becoming the smaller variety. That's not an accident, in fact. There's an infinite tower of these examples, but I'm not going to give you an infinite tower of examples. So in this case, Z is now the product of our modular curves. And so that's a surface, and we're going to put it inside a threefold, and the threefold is the Siegel threefold. So it's Siegel upper half space of for genus 2 billion varieties. Now, so that's three-dimensional. So that's why we have H3 here in the middle. And the class that we're going to take on our Siegel threefold is, again, a very simple Eisenstein series, what's sometimes called a Siegel-Eisenstein series. So it's an Eisenstein series associated to a character. It's a holomorphic function of weight 3, and it gives a holomorphic differential in exactly the same way that a holomorphic modular form gives a holomorphic differential on the modular curve itself. And then the projection here is I'm going to, on each of these factors, I'm going to project to the vector space associated to a new form F, and that gives me V tensor V, and I'm going to take the symmetric square part of that. So V tensor V will sort of decompose into the symmetric square of V plus the wedge 2 of Z, and I'm projecting to the symmetric square part. So this is now a three-dimensional space. This is one-dimensional, so now it's a four-dimensional kind of extension. And the relevant, again, they're in the world of sort of modular forms, there's a nice explicit formula that says that if I take one of these, the primitive of my Eisenstein series, and integrate it against my modular forms, or the two copies, I get an L value. In this case, it's the L value associated to the add 0 of F. So this is a particularly, if you wrote down Euler products with this L function as a product over primes, those polynomials in the powers of p to the minus s would have degree 3, which is sort of reflecting the fact that this is a degree 3 vector space. And so this is a pullback of a well-known integral, the pullback integral of an integral well studied by Rallis and Piatetsky-Shapiro and by Shimura and Shimura's students.
Which F bracket F?
So this is sorry, thank you. This is the Peterson norm of F with itself. And I've sort of included it here because one might ask, well, why don't I take two different modular forms, one on each copy of the modular curve, and you would get a Peterson norm of F with the other modular, say with G, and that'll vanish unless F and G are very closely related. So yeah. And okay, so as I said, there are in fact many other examples. In fact, there's an infinite family of examples that build that generalize the ones that we've written here. But hopefully I've at least convinced you that there's sort of a template for relating L values and extensions. And maybe very quickly, I will try to say, where does this lead? The point is that whatever extensions that we can construct in the Galois category, they can be organized into something which we call Euler systems, which was the focus of the Euler systems themselves of the semester, or one of the focuses of the semester at the Bernoulli Center that Philippe alluded to in his introduction. And in fact, that's where I began thinking about these kinds of problems. The first three examples that I gave recover known Euler systems, but the fourth example gives a new one. Since there are infinitely many examples of such sort of constructions of extensions, there are in fact, I think, infinitely many new Euler systems, which is kind of interesting because I think up to this point, we really only had finitely many examples of Euler systems, though they were expected to exist in great generality. The utility of Euler systems in number theorists is the fact that you can deform them to get connections with L values that are not necessarily zeros of the L functions. So you can prove things like this fact about 691 that I alluded to using the extensions that we constructed for Dirichlet characters. So the first example, I'm going to go through these slides very quickly. The first example that we looked at that recovers the Euler system for Dirichlet characters. This is a sort of well-known one. So it explains all of these L values, in fact. The second example recovers Rubin's Euler system for imaginary quadratic fields. And that Euler system can be used to explain the Coates-Wiles theorem, which was our first theoretical evidence for the Burt-Swinnerton-Dyer conjecture, and to give examples, as Rubin did, for elliptic curves with finite Tate-Shafarevich groups. The third example recovers Kato's Euler system for an eigenform F. And the fourth example gives a new Euler system. And so this is a theorem which is proved jointly by myself and my current PhD student at Princeton, Marco Sangiovanni Vincentelli, that there exists a p-adic Euler system for the adjoint representation of a modular form twisted by a finite character. And that Euler system can be related to a p-adic L function in some particularly useful cases. And maybe I should say that this gives a new proof, the existence of this Euler system, that the particular L value is the order of a p-adic Selmer group, which is closely related to the kind of L value that Andrew Wiles was studying in his first proof, or first attempt to prove Fermat's last theorem. I think I'll stop there.
Thank you. Wonderful talk. I have questions. Do you want a question? Yes.
So you've said you have a kind of infinite or type of instruction, or I presume for Euler system of this type. Perhaps you could say
What the?
You mentioned somewhere in the talk that there is an infinite tower of embeddings of varieties, which I presume give generalized Euler systems of the type you mentioned.
Yes.
Is that correct?
Yes. And yes, I can say Right. How? So for those watching online, if you're still with us, the question was whether I could explain this comment that there are infinite examples, and what are the, what's that sort of setup for the infinite examples? And so there's two actually families that one can look at. So one way to think about what's going on is one can look at SO in 2 and find SO in plus 1, 2. So the algebraic group SO, special orthogonal group, and signature N2 as a subgroup of the special orthogonal group N plus 1, 2. So stabilizing and anisotropic line. And in the case where N is 0, this is SO2, and this is basically the imaginary quadratic field. Inside SO1, 2, the corresponding Shimura variety is the modular curve. When case where N is 1, here's SO1, 2, so here's my modular curve. When I look at the corresponding Shimura variety inside SO2, 2, and SO2, 2 gives, for its Shimura varieties, either the product of two modular curves or some twisted version of that, like the Hilbert modular surface. When I take the N to be 2 here, I'm getting my two products of the modular curve. I'm getting SO3, 2, and that's PGSP4. So that's the Siegel threefold for its Shimura variety. So now you can consider a infinite sequence. Another infinite sequence that one can look at, and these are all, actually the development of both of these are works in progress for the Euler systems. And one can look at U and inside U of N plus 1, 1. And when N is 0, this is again the CM fields, so the over imagined quadratic field. And when N is 0, I get U1, 1, that's basically SL2. So that's the modular curve. And then as I change N, I'm going up a family of Picard modular varieties. And that gives a different collection of Euler systems. But the constructions that I laid out work. In each of these cases, the codimension of the varieties is 1. So everything works just as well.
One of my questions was stolen already. Another question.
Well, I have one more question. Okay. So I'm by no means a specialist in this area, so might have misunderstood something. But you constructed p-adic Euler systems, meaning that you are working with p-adic L values and this kind of type of process into that.
Yes.
And is there anything for the infinite place?
For the complex L values. So the question was, in the for the p-adic Eisenstein series, I thought I relate them to p-adic L functions. What about the connection to classical L values? So p-adic L functions generally have a property. The one, in fact, what you want of them is that at a certain set of points, they're actually interpolating the classical L values. And so once you've constructed these Euler systems and connected them to the p-adic L function, then we can move into a range where those interpolations make sense. And so we do get connections between values of complex L functions and the orders of certain Selmer groups. Yeah.
But it's not that one. I presume it's that one can probably not cover all the L values by this method. You have a restriction of the type of like negative even or something.
Right. There are restrictions on which complex L values one would expect. By complex L values means values of complex L functions that you would expect to see through some connection to p-adic L functions or through this kind of construction. And those are the so-called, more than just being the critical points, there will be sometimes called special points, but of course that could just mean anything. But there is kind of a characterization.
Thank you.
Sure. There was a, yeah.
The key part here is to show the non-vanishing of a certain special value of a p-adic L function. Is that right?
Right, or to connect. Ultimately, what one would like is just to have a construction of these extensions that you can very explicitly connect to values of a p-adic L function. And then you need, I mean, for that to be interesting, you would need to know that values of that p-adic L function, at least at certain values, are not zero. And in most cases, or the simplest cases, once you've constructed p-adic L functions, usually you can show that they're not zero somewhere. And when they're not zero somewhere, they're not zero really aside from maybe a finite number of points, or at least some Zariski sort of non-dense set of points or something. And so one can get some non-vanishing results out of that. So you don't need necessarily to know that every one of these L values is not zero or something, but there's usually something that's already known about the p-adic L function. It's the connection to the p-adic L function that's important.
Then, in terms of, okay, as an analytic number theorist, I have seen only points on the edge of the critical space so far.
Yes,
On the middle.
and I'm claiming facts about things towards the middle, perhaps.
So what you explained about periodic interpolation is what allows you to go to the middle.
Yes. So the constructions, so I should say, when does one expect such constructions to exist? You expect such constructions to exist precisely because some L function vanishes.
You should remove the eraser.
Ah, very well, very smart. And in fact, I would say we should expect, and this is more of a philosophical statement, that we can write down such constructions only when that L value, and that zero is a zero of order 1, because otherwise there should be an entire space of extensions whose dimension is the same as the order of the vanishing. And how do I know which one I should write down? So if I have a sort of systematic way of writing one down, I should have picked out a particularly nice extension. And I have no reason to believe that there's some preferred extension in that space. So I only believe that we're going to write down extensions systematically when the dimension is 1. So the order of vanishing is 1. And so there, the trivial zeros give me a class of such zeros. And so I'm looking at those extensions. Now that I've found those extensions, then I use the p-adic deformation to move to points related to non-zeros. Yeah.
Also, I have a last question. In all your examples, your test class was the kind of the simplest one you could imagine, Eisenstein series.
Yes.
So, are there non-custodial classes which give you interesting Euler systems, or what you can check are interesting or prove are interesting?
So the question is sort of, I seem always to be choosing Eisenstein series for my test classes, and that's true. Partly because I'm motivated by the integral representations I know for L functions, but and most of those involve Eisenstein series. But there are integral representations that don't. One example would be to take, instead of the Eisenstein series on the upper half plane, one could take a theta function associated to a Hecke character, well, of a particular infinity type. So like so associated, say, to a certain Grossen character. And there, one can still be very explicit about its class in cohomology, precisely because we know that on CM abelian varieties, that the de Rham splitting is or the Hodge splitting is algebraic. And so one can still be very, very explicit. And so then you get Euler systems associated to taking these theta functions, and this you can do, say, even on Shimura curves over totally real fields, and you can get. But this comes at the expense of varying only in anti-cyclotomic families, and so you get what's called an anti-cyclotomic Euler system. And the Eisenstein cases I've written down are what I would call a cyclotomic or even full Euler system. Um, they had some qualitative differences.
So in these last cases, we still think in terms of integral representation.
Yeah, so I'm looking to sort of, yeah, to sort of think of this as a very natural setup. So we have this integral representation. I want to sort of see this in some sort of expression of some fact in cohomology, and then go from there. So I'm always thinking in terms of the integral representation.
All right, so we can start. Okay, welcome back. So it's my pleasure to introduce our second speaker, Allan Sly. Allan moved from Australia to the US for his PhD at UC Berkeley. Then did a postdoc at MSR, came back to Berkeley as a faculty member before moving to Princeton University, where he's now a faculty in mathematics. Allan is known for having broken many problems in discrete probability, a long line of work in combinatorial optimization problems, where we connected computational barriers to phase transition from statistical physics, his settlement of the satisfiability conjecture, but also works that had implications in data science, such as for the block models of the perceptron. For these, he obtained numerous awards, in particular the MacArthur Fellowship in 2018 and the Loeb Prize in 2019. Unlike Chris Skinner, this is his first visit to Lausanne. But like Chris Skinner, he was supportive when we were working to restore the Bernoulli Center and send words of support, which we are greatly, very grateful for. Thank you for your support. I had the luck to be a colleague of his for many years and missed that. So we are very, very happy that you're here to present a new line of work, if I understand correctly, on infinite cycles in the interchange process in dimension 5. Allan Sly.
Does this sound okay? Okay, thanks so much, Emmanuel, and thanks so much for the invitation to speak here. It's a great pleasure to come and visit, and a great honor to be speaking in this Journée Georges de Rham. I unfortunately could not get de Rham's work into my talk, so I'll be talking about a model about sort of random permutations, or another way of looking at it will be sort of a random walk that interacts with its past. So called the interchange process. But first, let me start with something a bit simpler, which is shuffling cards. Everyone's familiar with, but this is going to be a really bad way of shuffling a deck of cards. So imagine you take your deck of cards, pick 2 of them at random, and just interchange their locations. And then pick another 2, interchange their locations, and keep going like that. This is a very slow way to shuffle a deck of cards, as you'd imagine. If your friend was shuffling the deck of cards like that, I'd maybe get different friends. But okay, so your very slow friend does this. How many times do they need to shuffle the deck? Well, Diaconis and Shashahani showed that you need a half n log n shuffles, where n is the number of cards in the deck. And this was a really important result in the sort of early theory of mixing times of Markov chains. It introduced the idea of using representation theory to diagonalize the transition matrix and sort of give upper bounds on mixing times. And it was also one of the first examples of Markov chains that exhibited what's called the cutoff phenomena. So if you do just slightly less than a half n log n number of shuffles, you'll be very far from the stationary distribution in terms of total variation distance. Whereas if you do just slightly more than a half n log n number of shuffles, it will be very well mixed, very close to a uniformly random permutation. up to some aperiodicity. So you get this very abrupt transition at a half n log n. Okay, so why is a half n log n the mixing time? Well, one way of seeing this, or at least a lower bound on this, is by looking at the number of by looking at the random permutation you get and looking at the number of cycles of length 1, because because a half n log n is the number of the transpositions you need to do in order to have every card have been in at least one transposition. This is the famous coupon collector problem. So before a half n log n, you'll have lots of cards that didn't move, and because of that, it won't be well mixed at that point. Okay, but after a half n log n, you'll get something that's very, very close to a uniformly random permutation. So you could ask, what does a uniformly random permutation look like? And in particular, what do its cycles look like? Well, there's about log n number of cycles, and the biggest ones are like take up a constant fraction of the n cards. So you get cycles of order about a constant times n in size. And you can say more about them. They have a Poisson-Dirichlet distribution, and the Poisson-Dirichlet distribution is sort of gives you a random way of splitting up a unit of mass. Actually, there's a parameter. This will be Poisson-Dirichlet with parameter 1. And it has a nice representation in terms of stick breaking. You take the unit interval, take a uniform point at random in that, then take the sort of right-hand segment, take a uniform point in that segment, take a uniform point to the right of that, and keep going infinitely many times. And I'll break up the unit interval into countably many segments. As you go to the right, the segments will get smaller and smaller, but the first few are sort of size order 1. And the size of the biggest, if you take a uniformly random permutation, divide the size of the cycles by n, then asymptotically their distribution will be like the sizes of these pieces in the Poisson-Dirichlet distribution. Okay. So by time a half n log n, this is what the cycles will look like. But actually, you'll get this behavior emerging even well before that point. So Bereshtiki and Duret show that actually there's a transition that happens when you only have n/2 number of transitions. So if you do slightly less than n/2 shuffles, all of the cycles in this random permutation will be small. Most of them will be size order 1, and the biggest will be of size order log n. But you do slightly more than n/2 shuffles, and you start getting large cycles that are of size a constant times n. So this kind of transition will be very reminiscent for people who've looked at random graphs or percolation before. You get a sharp transition between having only very small pieces to having some very large pieces. And this is exactly what's happening here. If I think of the cards as being vertices of a graph, and the interchanges that I do as adding edges in the graph, then the graph would be an Erdős-Renyi random graph. And this point n/2 transitions is exactly the point of the phase transition for the emergence of a giant component. Okay, so so a short time later, and it looks like actually before, but this is one of the things where some journals are faster than others. So the later work was published earlier. Schramm showed that the cycle sizes follow a Poisson-Dirichlet distribution, even in this sort of very early picture, once you've gone over n/2. And he showed something even more interesting, which is if you look at a sort of dynamic version of the process, you look at the sizes of the cycles as you do additional transpositions, what will happen is, well, each time you do one of these transpositions, if the cards were in the same cycle, then you would merge the two cycles together. And if the cards were in, if the cards were in different cycles, you'd merge them together. If they're in the same cycle, you'd split it apart. And so you can look at the cycle sizes and couple it with what's called a multiplicative coalescent and fragmentation process. This is a process where you have a set of masses that can either merge together or break apart. And the rates at which they do that are multiplicative. So if you have a mass of size p and q, they'll merge together at rate p times q. And if you have a mass of size p, it will split in two pieces at rate p squared. And so Schramm showed you could couple this process with the cycle sizes in this dynamical random transposition process, and also that the Poisson-Dirichlet distribution was the only stationary distribution for this process. Okay, so the interchange process that I'm going to talk about is like this random transposition model, but has an additional graphical structure on it. So I'll have some graph, and now each card will live on a vertex of the graph. And actually, I'm going to switch notation and say it's more standard to talk about particles on each vertex of a graph. So we have a different particle on each vertex of the graph, and now they can only swap when they're on sort of two ends of an edge. So we pick an edge at random, and then interchange their locations, and pick another edge and interchange them, and you keep doing this for a while. So these are shuffles, but now with a sort of graphical structure to them. And after a while, you get some random permutation, and now we'll be interested in the cycle structure of this random permutation. And I'm going to think about this in continuous time rather than discrete time. So rather than doing one transposition at a time, I'll sort of, on each edge of the graph, I'll have a rate 1 Poisson process. And when the Poisson process rings, I'll do a transposition on that. So it'll be happening as a continuous in time process. And the reason for that is I want to define this not just on finite graphs, but on infinite graphs. And things like the lattice ZD. Okay, so just to be more precise about the definition, you have a graph, a particle on each vertex, a Poisson process on each edge. When the Poisson process rings, you swap the particles from one side of the edge to the other, and we run this for time beta, and we get a random permutation. Yeah.
So is this one? No, you could do a big cycle. It's not for it.
Oh, indeed, yeah. So cycles can merge together or split apart. Yeah.
It's not obvious that there is a
Not obvious at all. Yeah. In fact, this will be an open problem. Okay. Okay. So you might say, why do I want to add a graphical structure to this problem? Well, the interchange processes come up in a few different areas. The first was work of Harris on exclusion processes, where it's sort of natural to look at. But the direction that will be I'll be motivated by is based on work of Balintov, and independently my colleague Michael Eisenman and Naktagali in the early 90s, where they connected this the interchange process to what's called the quantum Heisenberg ferromagnet. So the Heisenberg model is like the Ising model, if you know what that is. So rather than having spins that are +1 and -1, you have they take values in a sphere, and then we'll take the quantum version of that. And what Toth showed was that if you can understand a weighted version of the interchange process, so you get the you take the interchange process and then reweight it by the random permutation by a factor of 2 to the power of the number of cycles in it, then if this has infinite cycles in it, then that will tell you that you have spontaneous magnetization in the quantum Heisenberg ferromagnet, which is an open problem in this model of mathematical physics. Okay, so so he made conjectures about how the interchange process behaves, both with and without this extra factor of 2 to the power of the number of cycles. I should say that this is not sort of an unnatural thing to add. If you think about, say, the Ising model, or the random cluster representation of that, if going from a percolation configuration to the random cluster model is like taking a reweighting by 2 to the power of the number of connected components. So it behaves a bit like that. Okay, so Toth's conjecture is that essentially the behavior you get depends on the dimension of the that you're looking at. So we'll be talking about the lattice ZD, and the conjecture was that when in dimensions 1 and 2, you only see finite cycles for any value of time. Oh, and I should say, I'm using beta here for time, which is a funny symbol to use for time. The reason is that with the connection between the Heisenberg model and the interchange process, if beta is the inverse temperature for the Heisenberg model, then you would run the interchange process for time beta. So it's sort of natural with that connection. Okay, so in dimensions 1 and 2, the conjecture is that for all values of beta, you only ever see finite cycles. But in d greater than or equal to 3, there's a phase transition. At some critical value beta c, so for beta less than beta c, you still only see finite cycles. But for beta greater than beta c, you start getting infinite cycles almost surely. So this is when the graph is infinite. You could also take a large finite box in dimension d. And in that case, the conjecture is that the largest cycle will be fill a constant volume of the box, at least when beta is greater than beta c. Okay, so for dimension, okay, so why should you expect a different behavior in dimensions 1 and 2 and dimensions 3 and higher? Well, let's think about the cycle that contains the origin. It's sort of, the origin gets mapped to some vertex, which gets mapped to some other vertex, and so on. And you could say, well, maybe this is a bit like a random walk. If it was like a random walk, then you would get, you could ask, does it return to the origin? In dimensions 1 and 2, random walk always is recurrent. It always returns to the origin eventually. But in dimension 3 and higher, there's a positive probability that it never comes back. Okay, so that's one heuristic for why you might expect a different behavior in dimension 1 and 2 versus dimension 3. Okay, so, but let me first just briefly discuss what happens when beta is small, meaning that you haven't done too many transpositions. And in this case, it's very easy to show that you don't get infinite cycles, regardless of the dimension. I could take the graph and mark in red all the edges on which we've done at least one transposition. These are independent. So the red edges are just a percolation configuration. And the probability of them is 1 minus e to the minus beta, which is less than or equal to beta. So if beta small is small, it's like percolation with a small parameter, so it's subcritical. And therefore, it's known that almost surely all the connected components of red edges will be finite. but any cycle must be a subset of one of these connected components of red edges, because you don't do any transpositions, from the component to its complement. So therefore, all the cycles must be finite as well in this case. The percolation threshold is not the right threshold for the existence of infinite cycles, but it does give a lower bound on that. Yeah.
And for the previous argument, you said take 0 as an example, but otherwise you just need to not go back to where you were, and that's still the 3 that it happened. Is the right threshold or not? I mean, there's no formal random walk associated to it. Okay, we'll see.
Yeah. So I'm not quite sure.
So the fact that it's not specifically 0, just not intersect with history and that.
Yeah. So we'll come back to sort of like the way in which this walk interacts with its history is going to be really important for us, and so that's definitely something I'll be talking about. Okay, so since Toth's conjecture, there'd been various work on this on a range of different graphs. Beresicki, Durrett, and Schramm's results correspond to the complete graph. Omer Angel and Alan Hammond gave a fairly complete understanding of what happens on infinite trees. And more recently, there's been work on the hypercube and the Hamming graph and random regular graphs. So all of these graphs are ones which sort of expand very nicely, but which is not the case for the lattice. So none of these results apply to the original conjecture about ZD. So the result I'll talk about is what happens in dimension 5 and higher, and showing that for all beta sufficiently large, we do indeed get infinite cycles almost surely. And in some more recent work, which we're just in the process of writing up, we've also can talk about what happens in finite boxes and show that the largest cycles fill up a constant fraction of the box and also follow the Poisson-Dirichlet distribution. Okay. So one thing you might notice about this result is that 5 is not the same as 3. So we're missing dimensions 3 and 4. And so why were we not able to do those, or what makes things easier in dimension 5? Well, the higher the dimension you're in, essentially the more space there is. And this comes back to Emmanuel's question about essentially the random walk running into its past. So what's special in dimension 5 and higher is that if I take 2 independent random walks and look at their future trajectories, there's a positive probability that they never run into each other. Their paths are completely disjoint. And this is not true in dimensions 3 and 4. But so if I think about a random walk with both an infinite future and past, this is the same as saying that there's a positive probability that its future after time 0 never runs into its past before time 0. And that's only true once you're in dimensions 5 and higher. And that's going to be very important, I guess. Okay. So yeah, so I've been saying that, it's like we're looking at a random walk. I want to be a little bit more specific about what I mean, and what we call the cyclic random walk. So we want to know the cycle of the origin. So we'd start off with the particle at the origin, and it's involved in some transpositions. So it's jumping to neighboring vertices. And this is effectively just doing a random walk up to time beta. And that will give us the first location of the cycle that it's in. And then if we want the next term in the cycle, we should look at the particle starting at that point and follow its random walk. And then and then follow the trajectory of this particle. So it's like looking at one particle from time 0 to beta, the next particle from time beta to 2 beta, then 2 beta to 3 beta, and so on. And so ultimately what we'll want to show, let me say, for each of these sort of colored segments is just the trajectory of one particle between time 0 and beta. And these are exactly just continuous time simple random walks. So very nicely behaved. Unfortunately, they're not independent of each other because they're generated by the same set of transpositions. And so they share some randomness. But what we want to show is that on large time scales, this path looks morally a lot like a random walk. And that will be the goal of this project. Okay, so I can give a different representation of a cyclic walk, sort of more graphically. So I'll put the graph on the x-axis, and just to make things easier, I'll let the graph be z. And then for each vertex, I'll have a vertical line representing time. And so if I want to, I'll place a horizontal red line every time we do a transposition between two of those vertices. And now because it's cyclic, I'll repeat the same pattern every time beta. Okay, and now if I want to work out where the path goes, I just draw a line where I go up, and every time I hit a red line, I jump to the other side and go up. And so you can follow where the path is going. And so 0 gets mapped to 1 at time beta, -2 at time 2 beta, and then back to 0 at time 3 beta. So in this example, it's in a cycle of length 3. But now to generate this picture, or where the walk went, I didn't really need to know all of the transpositions everywhere to do it. I only needed to know where the transpositions along the path was. So if I wanted to say what's happening from time 0 to beta, I only really needed to look at this part of the space of the transpositions to figure that out. This is a random set, but I just need to explore that segment. Okay. Now let's see what happens between time beta and 2 beta. Well, I've already revealed this part of the space. So then in this first sort of segment of time, I know that there's no jumps to the left because I've already revealed that down here. So as I'm going along here, I might jump to the right, but I know I won't jump to the left until I get up to here. And now I know I have to jump to the left. So, and so what we'll need to do is kind of keep track of what information we've revealed as we go along. And so now if we're at time, say, 3/2 beta, we'd reveal this sort of extra yellow bit of information, and we'd be here. Now we don't know what's going to happen in the next little increment of time. So we're not being affected by the past of the walk. And so it should just behave like a regular simple random walk after this. And so a lot of what we want to do is to sort of understand the times at which we're sort of not affected by the past by keeping track of which part of this Poisson space that we've revealed. And to make that more precise, we say that the walk is interacting with its past if there's an integer multiple of beta such that the distance from its current location to its past location is equal to 1. And that means we'll have sort of revealed some information about what happens next in the path. If this was exactly equal to 0, that would mean that we've already closed up a cycle and we're just sort of going around and around, just keep going around and around. But when this difference is greater than or equal to 2, it means that we're not interacting with our past. And so the future evolution of the walk, at least for the next little bit of time, will just behave like an independent, simple random walk. So at these times, so there'll be times where the past doesn't matter in terms of working out what happens next. Okay. And so we want to sort of understand these. Okay. So now I want to sort of give a summary of how you might sort of understand or like approach this sort of question. And so what we said was that in 5 dimensions, we're hoping that the cyclic walk behaves like a random walk. If the cyclic walk did behave like a random walk, then in 5 dimensions, we know that it's not going to interact with its past very much. The future will tend to not be in the same places as the past. So if it behaves like a random walk, then it doesn't interact much with its past. But on the other hand, if it doesn't interact much with its past, then it should behave like a random walk. Okay, so this is what I call a circular argument. And unfortunately, in maths, you can't just be finished with that. Okay, so how do you turn a circular argument into an actual proof? Well, the natural sort of thing is to do induction, to sort of say that you have this sort of behavior on one time scale, and then try and inductively prove that on bigger time scales. So, so a sort of multi-scale induction on time scales. And we want to say that, and roughly what we'll want to say is that if the walk is behaving nicely, then if we look at a sequence of segments along the walk, those will be close to independent of each other. And if they're close to independent of each other, if we're adding up a bunch of independent things, that should look like Brownian motion. And so behave like a random walk. On the other hand, sometimes things will go wrong, and we'll have to deal with what happens when the walk gets sort of badly tangled with itself. Okay, so, that's the wrong way. Okay, so this will be a multi-scale induction, and part of the essence of multi-scale inductions is that, you know, a lot of the art is in making the right definitions and inductive assumptions. So I'm afraid I have to make some definitions. One is that we don't want the walk to spend too much time in one area, because if it did that, then it's likely to interact with itself a lot. So I'll say a block of side length L is heavy if the walk has spent more than time L to the 2.1 there. Okay, now if we're just taking a simple random walk, if it enters a block B, the total amount of time you expect it to spend there is L squared. And the probability of it spending time L to the 2.1 there should be very small, at least if L is big. So this is so we shouldn't see heavy blocks if it's behaving like a random walk. Yeah. 2.1 is just any number just a number a bit bigger than 2.
Okay.
Yeah. So probably, yeah. I guess I'm making my slides in PowerPoint, and it's easier to write 2.1 than epsilon in in PowerPoint. But as a former Microsoft employee, I still feel obliged to continue using PowerPoint. I also like it more for pictures and things, but okay. And so the other definition I want to say is that at time t, if we look at a ball centered around sort of WT, the location of the walk, then we'll call it relaxed if all of the blocks centered around WT are not heavy. And I'll have a slightly different definition for small values for small scale blocks, but basically that's essentially it's a place where none of the blocks around it are heavy. And why is that? Why is being relaxed good? Well, it means that the history of the past is sparse enough that at least a simple random walk can easily miss it. Really, this 2.1 could have been anything smaller than d minus 2, actually. So here it's a number, in dimension 5, it's some number between 2 and 3. And so if you have a relaxed time, and then you start a simple random walk from that point, then there's a good probability that the simple random walk will never intersect the history of the walk up to that point. It's sort of sparse enough that it's easy for random walk or Brownian motion to miss it. And this is the key place that we're using that the dimension is at least 5. It wouldn't be true in dimension 4, say. Okay, and now we want the same to be true for cyclic walks. So the most important inductive hypothesis for us is about transition probabilities. The probability that the cyclic walk ends up at a particular vertex, we want to be at most, at time s, should be at most s to the minus d over 2 plus epsilon. So here, I guess I did work out how to write in plus epsilon. But okay, so if it were just a simple random walk, you'd have this without the plus epsilon, and this is just to make our life a bit easier. And I should have said the induction will be on scales growing like 4 to the n. Okay, so we want this transition probability estimate up to time 4 to the n. And if we had that, what it would say is that if we're at a relaxed time and then we run cyclic walk after that, there's a probability, a constant probability that it never interacts with its past. So you can break up the past and the future into independent chunks. This, by the way, also if we had this, we could just add up the probabilities of it ever returning to the origin at a multiple of beta, and show that that was less than 1. So if we knew this also, this would finish the proof that you have infinite cycles. You'd have a positive probability of never returning to the origin. Okay, so but now, to make our life easier, I'll throw in some more inductive hypotheses. One is that the walk looks a lot like Brownian motion. We could couple the walk and Brownian motion such that they're very close together, except with some really small probability, e to the minus n squared. Additionally, up to time tn, the fraction of times that are relaxed will be at least something a bit bigger than 90%. And finally, what we call the pair property, if we take, if we start cyclic walk from 2 points and assume that they don't merge together or form cycles, then the fraction of time that they're close to each other is going to be fairly small. So they don't, pairs of cyclic walks don't tend to sort of hug close together. Okay, so all of these properties are very hold if we replace cyclic walk with just simple random walk, and they're very easy to show. But now our cyclic walk up to time beta just behaves exactly like simple random walk. So we sort of automatically have the base case of this induction up to times beta. Okay, so so how do you put that together? Well, what we'll want to show is that as I sort of alluded to before, that we can sort of add up independent cyclic walks and get something that's close to a longer cyclic walk. So let's suppose we have cyclic walks of length 4 to the k and L of them that are just independent of each other. And then we concatenate them together into a longer walk. So these were just independent. So the distribution of this longer walk is not a cyclic walk of length L times 4 to the k, because of, the future and past can interact with each other a bit. But what we want to show is that it's close. that we can sort of couple a length L4 to the k cyclic walk with this concatenated one. And these concatenated pieces, they're, what am I trying to say? Then this is like summing a sum of IID terms, and sums of IID random variables are like Brownian motion. So if we knew this, that we could sort of concatenate like this, then we would get a path that looks a lot like Brownian motion, which is what we need for the induction. So in fact, if we could show that, then if we can show this sort of lemma, then it's really not much work to prove all of the inductive hypotheses in the from there. So this is really the main thing that we need. And so what we sort of hope is that at this sort of junction point where we're concatenating two independent cyclic walks, if this were a relaxed time, then there's a good chance that this future trajectory doesn't interact with the past, and then then there's the coupling. You can couple them together exactly. But there's also a chance that that doesn't happen. So then you could wait and so what we'll show is that you only have to wait a short period of time until you get another relaxed point in time. Hopefully at this one, you can sort of couple the future so that it's sort of independent. And maybe that fails again, but the number of trials that you have to do is small. And so the total error that you get in this coupling will be something like the total of length to the power of epsilon, something very small. So it really will look like a sum of independent segments of cyclic walk, which is like a sum of IID random variables. Okay, but that's sort of what's happening when things are good. Things can also be bad. You could have a cyclic walk that's sort of coming along, looking nice, and then you run into some sort of tangled region. It sort of wraps around itself in some very complicated way. And then it's no longer the case that you can say that, oh, well, the future is going to be independent of its past, approximately. It could be that, you know, its past sort of very strongly affects what happens next. So and then if we don't have control over what it does next, maybe this tangle sort of keeps growing, and maybe it, you know, keeps growing and growing, and eventually comes back to its starting point, and you close off a cycle. Okay, so this would be bad for us. We need to be able to sort of deal with sort of bad configurations of the cyclic walk before they get even worse. Okay, so we need to be able to escape. And so we're going to sort of show that these tangle regions get confined to sort of very sort of local spots. So imagine we have some messy region here of side length L, and now I'm going to draw a grid around here of boxes on a much smaller scale. So like side length M equals log L to the power of 100. Okay, so these green ones are much smaller. And what I'm going to claim is that each time I enter one of these green boxes for the first time, I have a very good chance of being able to escape and sort of get away from this tangle pretty quickly. So suppose we look at one of these green boxes and I put its side length M, and I put, say, square root M number of points in the middle. And I just reveal the cyclic walks starting from each of them one at a time. Because this is in dimension 5, we don't expect these to run into each other, but maybe a few of them do. But we're likely to get, say, at least one here that sort of quickly moves away from the box and sort of gets us away from the tangled region. And essentially, these are each independent trials. So the probability of them all failing should be like e to the minus a constant square root of M, which is something really, really small. So essentially, in any local neighborhood with very, very high probability, there'll be at least a few kind of escape routes if you can get to them. So we enter one of these boxes. There's at least one escape route from it with very high probability. And now we haven't revealed anything yet inside this box. So so what it does next is like just a sort of independent cyclic walk, and there's some chance that it sort of hooks up with one of these escape routes. And the probability of that is maybe like m, the side length to the power of minus a constant, which could be quite small, but it's not too small for our purposes. So there's at least a okay chance of being able to escape. And so we sort of enter this box and then escape a long way away. But maybe we failed and we sort of quickly came back. Then we could say, okay, well, we'll enter a different green block, try again. Maybe this one also failed. But then if we do enough trials, eventually we'll have a success. And the number of trials we'll need to do is essentially m to a constant, which is polylog of the size of this box. So the total amount of extra of time that we spend doing all these excursions will only be like L times polylog of L. So, and that will be not enough for this tangle to really grow any bigger. Okay. So locally, there's sort of still lots of options to be able to escape. Okay. So if you haven't encountered multi-scale probabilistic proofs before, which probably many of you haven't, there's one sort of key idea in this, which is that, okay, the challenge is the probability of something bad happening is getting smaller on every as you go to bigger and bigger scales. So that means that the chance that something failed on a smaller scale is bigger than what you want to prove on a higher scale. So you have to be able to deal with a few bad events happening. And typically a way of dealing with this is through a sort of spatial independence. So let's split the grid up into blocks now of length Tn to the epsilon. And we'll say a block is bad, marked in red, if essentially the inductive hypotheses don't, like the events in the inductive hypotheses don't work in that case. So maybe paths don't have lots of relaxed points on them, or they don't look like Brownian motion. So the probability of a single of these blocks failing by the inductive hypotheses is about e to the minus epsilon squared n squared. So it's still very small. It's still unlikely to see any bad blocks in a sort of reasonable neighborhood that we might visit up to time Tn plus 1. But the probability is much too big for our inductive hypotheses. On the other hand, if you set the events up in the right way, blocks that are sort of at least not adjacent to each other will be independent of each other. And so the probability of having lots of these bad subblocks will be much smaller. So it will be, so the probability of having, let's say, epsilon to the minus 5 number of these bad subblocks will be like e to the minus 2 n plus 1 squared. So we might have these bad subblocks, but we only have to deal with order 1 number of them. So they're and this is typically what you see in multi-scale sort of arguments. It's like actually it was summarized to me as by Gadi Cosma as a sort of multi-scale arguments all look the same. It's boxes within boxes within boxes. And the key is to like how you define what the boxes are and the definitions, and that sort of you have to be able to deal with a few small boxes, bad boxes on smaller scales. Okay, so And the key estimates we'll need are one, that we don't see any heavy blocks, and two, that we never have to wait very long until we get to a relaxed time. Okay, so, and the fact that we don't see heavy blocks is going to come from this essentially, this sort of escape procedure that I described before. So, so we start off, so a walk enters B, we start this escape procedure in some small subblock here, and maybe it sort of escapes and never comes back to B, and then it won't have spent too much time in B. But maybe it didn't, and you sort of loop around and come back. Well, then we'll just try this again. Maybe that one fails. But the idea is that you only have to try a few times before you'll sort of escape away from B and never come back again, at least up until time Tn later. And so the total amount of time you'll spend in this box is like, if it's side length r, would be like r squared times polylog r, which will be smaller than r to the 2.1. So any block that's at least Tn to the epsilon will not be heavy with very high probability. Okay, so there's nowhere where the path is going to, the cyclic walk is going to have spent a long time around. Okay, and now we want to show that you quickly reach a relaxed time. So to be relaxed, recall that means that at we look at the walk at time, let's say S prime, look at a box around it, and say that, and we have to say that this box is not heavy. We've just ruled out sort of all of the big boxes being not heavy, so we only have to worry about the small boxes around it. If we were in a bad subblock, maybe that's hard to do. Maybe we can't say much about that. But there's only a few of these bad subblocks, and they're not very big. So we just can't spend very much time in them before exiting and being in a good block. And now when we're in a good block, one of our inductive hypotheses was that if we look at the path along here, then there's lots of relaxed points along that. But that means relaxed with respect to sort of the recent history of the past. We also have to worry about, you know, the sort of ancient history of maybe the path visited this blocker sometimes before. Okay, but our argument about heavy blocks said that basically that this didn't happen too many times. And our inductive hypotheses about pairs of paths said that two of these paths won't spend too much time too close to each other. So we'll be able to find a point on one of these paths that's sort of that's relaxed and not close to any of these sort of ancient paths, and therefore this will be a fully relaxed time. And so you don't have to wait very long to get to relaxed paths or times. And that's exactly the property that you need to be able to show that when you concatenate smaller cyclic walks into a longer one, that you can couple those with sort of very low error. And so therefore the cyclic walk will behave like a sort of sum of independent things, and so look like, so be approximately Brownian. And that's what we need to sort of prove all the inductive hypotheses.
Inductive hypothesis of the pairing thing is for that argument only?
So for I guess for the inductive hypothesis of the pair process, we need that they, you know, don't spend too much time or that they separate at some point, and then there's a good chance that they'll sort of diverge away and not visit each other too much. Yeah, and so and essentially because this will hold for like the pair property holds for two independent Brownian motions, and our estimates will sort of say that these paths behave like two independent Brownian motions, then they won't spend too much time close to each other, except with very small probability.
So basically, you mentioned that the concept of relaxed means
Yeah.
that you're not spending too much time in the recent past.
Yeah.
And then, how do you guarantee that in the distant past you're not spending too much time in the box?
Yeah, so a box on so this box B is large enough that we know that there's no heavy boxes on that scale. So we only have to worry about sort of smaller scale boxes around here. So as you say, they're sort of relaxed with respect to the local history. And then we have to worry about these sort of ones from the more distant past. And what we can show is that you'll find that sort of on the scale of boxes that you have to look at, you can find some points in time along this path such that these ancient ones don't intersect, none of them intersect that. And that's a combination of the pair property and the fact that there aren't too many of these ancient paths. And so if you put that together, you'll find times where this is really both separated from the ancient history and a relaxed point with respect to this path. Okay, so that's sort of enough to establish the existence of infinite cycles. You can also ask about what's happening in finite-sized boxes. So we'll imagine we have a box of side length L. We could try and run the same argument, but eventually the cycle is going to start filling sort of quite a bit of the box, and things will start to get heavy. And then these arguments will break down. But you could ask sort of how far you could push it to. So, okay, I might need to change the parameter of 2.1 that I had before. And if I did that, I could sort of run the argument up to L to the d minus 2 minus epsilon. So if d equals 5, this would be time L to the 3 minus epsilon. The box is side length L. So we could show that there are cycles of length a bit less than L cubed. But we want to show that there's cycles of length L to the 5. So that's not enough. So what we're going to do is look at, say, two paths of this length, say L to the 3 minus epsilon, and look at how much time they're adjacent to each other. So just track them up to that time and look at how many times they sort of get close to each other. And to do this, essentially what you need to do is get much more refined estimates of transition probabilities. And say that, well, after time L squared, they're basically in a uniformly random location, because L squared is the mixing time of a random walk on this box. And the fraction of time that they'll spend adjacent to each other will be concentrated around their length, so t squared divided by n. Actually, there's an extra constant factor there. Okay. And now if I had two longer cycles of length p and q, I could say, well, I could break them up into segments of this length and say that the total number of times the first cycle is adjacent to the second cycle is going to be concentrated around p times q divided by n. Okay. And now, to finish things off, I'm going to sort of slightly adjust our value of beta. Beta is the, and slightly adjusting beta is the same as sort of adding in a few extra transpositions. And so each time I add in a transposition, it will either merge two cycles together or split two cycles apart. And what's the chance of it merging two cycles together? It's the number of points on which those cycles are adjacent to each other. And we've just sort of understood how many there are, and it's proportional to the product of their lengths. So again, you get a sort of multiplicative coalescence and fragmentation process. So in this, the same as the one Schramm studied in the setting of the complete graph. And so if you run this for just a really small change in beta, the cycles will sort of merge and fragment, and it will converge to a Poisson-Dirichlet distribution. And so in particular, one can show with this that you'll get cycles that fill a constant fraction of the volume. Okay, and so there's lots of things that we don't understand. Dimensions 3 and 4 are completely open. Dimension 4, you could expect maybe the same kind of approach might have a chance, because in dimension 4, two independent walks will still definitely intersect each other, but they don't do it very many times. So you might expect that the sort of interactions with the past are sort of few enough that they don't change the overall behavior. Dimension 3, on the other hand, three-dimensional random walks their paths intersect each other a lot. You would have to do something quite different there. Another question is showing that there's no infinite cycles in dimension 2. I should have said in dimension 1 there's no infinite cycles because you never percolate in dimension 1. So the simple argument I gave ruled out ever having infinite cycles in dimension 1. There's no monotonicity in beta, so it's not clear that you have a critical value of beta where which was part of the conjecture where, so for beta less than beta c, you have no infinite cycles, and beta greater than beta c, you do. It could in principle be the case that, as you increase beta, first you don't have any infinite cycles, then you do, then you don't, then you do again. We don't know how to rule that out. Alan Hammond, in work on the interchange process on trees, showed that on sort of trees with big enough degree that you do have a critical value. So it's possible that some of those methods might work. And then finally, there's the extension of this to the quantum Heisenberg ferromagnet. So where we weight cycles by a fact, or the permutations by 2 to the number of cycles. There's more complications with this, and you don't have the same kind of independence that you do in the regular interchange process. But there's also reasons to think that some of our approaches it might be possible to understand this one. And finally, I mean, this is really a result about random walks that interact with their past. Well, actually, I'm sorry, I'm out of time. I should stop now. Thanks. Martin?
Question? Yes. Go ahead. So if I understood correctly the analogy with the quantum Heisenberg, so this here 2 is the lower critical dimension, is 4 is the upper critical dimension, and so it's 4. We still expect a Gaussian description of the
Yes. Yeah.
But in 3 we expect critical exponents non-trivial. So at least in the quantum Heisenberg here, would the critical exponents be different for this version? Is that an understanding what is the still theoretical description of that?
Yeah, I don't want to claim to know anything about what happens in 3 dimensions. I think that's that sort of looks, yeah.
But are there numerical simulations that compute on critical exponents to try and trivial?
I'm not sure. That's a good question.
Question. Yes.
You work on the intergalactic with a very specific graph.
Mm.
Increasing the dimension brings nice properties.
Yeah.
And, it's the case that in some measurable way, we're getting closer to a new standard. At least for finite properties.
So I mean, locally, like as you increase the dimension, the walk should be more and more like a walk on a tree. So I mean, some of these arguments, some of these questions. So I'm not sure if I can give a precise sense in which you know, that's the case, but yeah. I mean, for example, in terms of this question about having a you know, a critical time beta, there it's been proved on trees, and when the dimension is high, the lattice is looks sort of more like a tree, sort of morally, and so you might hope that the same sort of methods apply there, but I don't think I have a sort of more concrete sort of description in terms of that. Yeah.
Particularly interested in one question. So if you take a KD graph from a group,
Yeah.
Is there any kind of interpretation of relation to? So you mentioned a lot like random walks and graphs.
So
Your setting can also is in a sense KD graph, or maybe there's no connection.
I mean, where the underlying graph is the Cayley graph?
Yes.
The
underlying graph is the KD graph.
Yeah. So what I suspect is that the property that's going to be important is on the underlying graph, do two random walks sort of intersect each other, and this will depend on. I mean, I think you know, for most groups that are not sort of, or that are like higher than 4-dimensional, that should be the case. Yeah, so I mean, it's you know, certainly it's interesting to think about what could happen on, you know, like other groups or other graphs in general, and we haven't thought about that yet.
So in this, as you mentioned, in this quantum Heisenberg, you
Yeah.
replace the item ±1 by a point on -2.
Yeah.
There's a general, I mean, you can take a d-dimensional field. Where did this choice of the dimension of the sphere appears in the math? Is it the weight of the cycle?
I am more a sort of just a consumer of this connection, and so I mean, you know, Balintov did this work, and then went around the probability community promoting this interchange process, and Yuval Perez was also very interested in it and sort of advertised it a lot. Yeah, and embarrassingly, I hadn't opened you know, Balint's actual original paper until we started like writing the introduction to the this paper. But so I don't have the answer to that. I'm sorry.
Very good. You have enough negative, so I'll ask a question afterwards. Let's thank Allan again.
Sorry,
Amazing.
I